So in this video, we're going to talk about solving limits with algebra. So we already looked at directly solving limits, right, with direct substitution. And we've looked at how we can find limits, really approximate limits via tables and via graphs. If we want a more exact method, we need something like direct substitution, but sometimes the direct substitution doesn't exactly work. So a simple example of that, let's just say we want to find the limit as x approaches 1 of x squared minus 1 over x minus 1. So what happens here is that if we try direct substitution, we're going to end up with 1 squared minus 1 over 1 minus 1, which is going to be 0 divided by 0, right? And this is what we call an indeterminate form. Okay. So this is a little bit different than a different number divided by 0, like 5 divided by 0 or 1 divided by 0. In this form, we say it is indeterminate, whereas with a different number, like something like 5 divided by 0, we say is undefined. And the difference hasn't really mattered up to this point, but this will kind of inform what the limit is going to look like. So in an indeterminate form, this is usually a clue that we can do some kind of algebra and maybe do some cancellation, maybe just some kind of manipulation where we'll be able to actually get an answer for the limit via direct substitution. Whereas an undefined form, or just, undefined number, this is usually a clue that there is a limit at infinity, meaning that the limit as x approaches 1 is infinity or negative infinity. Or maybe from the left side it goes to one of those, and from the right side it goes to the other one, right? Either positive or negative infinity. Either way, we say the limit doesn't exist. But the top form, the indeterminate form, this is a hint that we could get an answer. And this should also make sense if you remember the graph of this function, which I don't think we looked at this one, but we looked at a similar one. It might have been this one. But regardless, if we look at x squared minus 1 divided by x minus 1, it just looks like a straight line. But the key point is that 1 here, right? And we see if we click on this, it says that 1 is undefined. So regardless, it still looks like the limit would be at that point though, right? That the limit is going to be equal to 2. So maybe through the use of algebra, we can actually find that the limit is indeed 2, rather than having to come look at the graph or look at a table or something like that. So let's go ahead and see what that would look like. So we'll go ahead and just do some algebra, right? X squared minus 1 over x minus 1. So of course, hopefully at this point, you recognize that this is factorable as x plus 1 over times x minus 1 and over x minus 1. So we go ahead and cancel these terms, and we're just left with x plus 1. Okay. So again, these two things as functions are not the same, but this is what the graph looked like, right? It looked like the graph of x plus 1 minus 1 point. So the domains of these two things would be different if we're thinking about them as two functions. But in terms of the limit, this is how we can actually find what the actual limit is. Okay. The limit really is not concerned with the domain, right? We've seen several instances where the limit is different than the output of the function, and we can define a limit at an x value which is not in the domain, right? It just needs to be defined around the domain. So if we go ahead and do the limit as x approaches 1 of x squared minus 1 over x minus 1, this is equal to the limit as x approaches 1 of x plus 1, as we just showed, which is equal to 2, because now we can do the direct substitution, right? So And this confirms what we saw on the graph. So now this will let us get an exact answer and be 100% sure of it rather than having to approximate with a graph or table. So we'll do a few more examples here. So a lot of these will just boil down to factoring something, but there are some other techniques we can use as well. Let's do one more factoring one first. Okay, that's kind of the first thing we usually want to look at, especially with these rational functions. So we typically, when we get something like this, we do want to factor it, but you do want to first do the direct substitution, because you need to make sure that you do get that 0 over 0 form, that indeterminate form. It might be set up to look like this, so you kind of get in the pattern of factoring and canceling things out, but then you'll go back and see that, oh, you could have just done direct substitution the whole time, so you did much more work than needed. So it's always good to plug the number in first. So we get 3 squared minus 3 times 3 over 2. 3 squared minus 5 times 3 minus 3. Okay, so the top is 0 because we have 9 minus 9. The bottom here we have 8 times 2 is 16 minus 15. Oh, I'm sorry. This is 3 squared, not 2 cubed like my brain said it was. So this is 9 times 2, which is 18, minus 15 minus 3. So this will be 0, right? So 18 minus 15 minus 3. So we get 0 over 0. So now this is a hint that there's some algebra we can do. In this case, it'll be factoring. So we'll go ahead and do that. So we get the limit as x approaches 3 of, we can just go ahead and do the factoring now. X times x minus 3 on the top, right? We can pull an x out of both terms. On the bottom, this will be a little bit trickier. We have to assume one of these is going to be x minus 3, otherwise what's canceling? So I'm just guessing this right now, but that's going to make this have to be plus 1. And let's see if that works out. So 2 times negative 3 is negative 6, plus 1 is indeed negative 5. So it looks like everything is good here. So we'll have these canceling right here. So this is the limit as x approaches 3 of x over 2x plus 1. So this is going to be 3 over 6 plus 1, which is 7. Okay, so we get 3/7. So this is a good example of, where this would be hard to read off of a graph, right? 3/7 isn't a nice number. It's a infinitely long decimal with a weird pattern that repeats. So it would be hard to recognize that on a graph or a table that it's going to that number. And so this gives us a better information about where exactly that limit is. Okay, so now let's do one where we don't necessarily need to factor. Maybe we need to do something else. In general, there could be a lot of different things we can do, a lot of different algebraic rules, anything that, we've looked at so far, we could invoke here. This is an example of one that's actually a bit different from really anything that we've done, but it is a common technique, so it's good to look at now. This technique comes up in a bunch of different things. So this is what we call multiplying by the conjugate. So just for a moment, we'll go off to the side here, and let's remember the formula, which I'm sure we're familiar with by now. A plus b times a minus b equals a squared minus b squared, right? We've already seen that formula in this video, for example. So what we don't normally do is start from the first line and go to the second line, right? We're usually going the other way. So what does that have to do with anything here? Well, first of all, let's just go ahead and do the direct substitution just to make sure that we do get that 0 over 0 form. So this is going to be -1 plus 2, which is 1 on the inside there, over -1 plus 1. Square root of 1 is 1, so that's 0 over 0. So now we go ahead and look, okay, there must be some algebra we can do, but there's no factoring that we can do, right? So one thing that's common with square roots is if you have a square root in the denominator, it's common to what we call rationalize it, which is where you multiply both the top and bottom by that thing in the square root. So here we want to do something similar, but we want to multiply by what's called the conjugate. So if you have a term a plus b, its conjugate is the term a minus b, and vice versa, right? So if you have a term a minus b, its conjugate is the term a plus b. This is helpful in cases where we have things like square roots. So let's go ahead and do it, and we'll see why that's helpful. Okay. So when we do this on the top, now we have this formula, a plus b times a minus b. So this is x plus 2, square root of x plus 2 squared minus 1 squared over, we'll just leave the bottom. We won't multiply it out yet, mostly because I don't have room here, but we don't need to do it yet. Okay. So the square root of x plus 2 squared, the squared and the square roots are inverse functions, right? They cancel out. So we get, if we want to be really proper, that limit should be coming along with us. Okay. So the limit as x approaches -1 is of x plus 2. 1 squared is just 1. Now I'd say it's probably a good idea to multiply out the bottom. It might not end up being necessary even, but there could be some kind of simplification that we can do down here. Okay, so get plus x plus 1. Okay. So on the, actually, I take that back because now I see where this problem is going. Let's go ahead and leave it factored because as maybe you already noticed, the top now is going to be x plus 1. So that's what's going on here, right? That term is going to cancel out. Okay, so the top is x plus 1 now. And the bottom is x plus 1 times square root of x plus 2 plus 1. And now these cancel out. So we are left with the limit as x approaches -1 of 1 over the square root of x plus 2 plus 1. I don't know why I had that all in the square root before. Okay. And now we can go ahead and do that direct substitution. Okay. So this will be 1 over, this is going to be 1, like we already saw, plus 1. So this is going to be 1 over 2, 1/2. Okay. So, like I said, this is a pretty common technique. When you have, especially rational functions that involve square roots, a good way to kind of change the problem around, whether you're actually like simplifying it is, sometimes you're not really, but it at least will change the problem around, and maybe, give you a different form that's more useful. Of course, this is justified as we saw with the rational functions, because this is something divided by itself, so we're multiplying by 1, meaning we're not changing the fraction. Okay, so we've seen examples now where we solve by factoring, solve by multiplying by the conjugate. So let me go ahead and label that. Multiplying by the conjugate. Okay, so this is that word conjugate in case anybody wants to look that up or anything. Now let's go ahead and do one with an algebraic technique that we have seen before, which will be simplifying a complex fraction. Okay, so now we're going to look at the limit as x goes to, let's do -3 over 1, or of 1 over x plus 2 plus 1 all over x plus 3. Okay. So we saw how to deal with complex fractions before, meaning that we have a fraction within a fraction. So we essentially want to first, wherever that complex fraction is, it might be in both the numerator and denominator, we will want to first find the common denominator in that part of the fraction. Okay, so here we're going to multiply the 1 term by x plus 2 over x plus 2, right? Because that's the denominator of the other term. So we'll get the limit as x goes to -3 of 1 plus x plus 2 over x plus 2 over x plus 3. Okay. And now we can go ahead and do 2 steps here at once. First of all, we can just add the 1 and the 3 on the top here. So that's x plus 3 over x plus 2. And then we're dividing by x plus 3. So this is the same thing as multiplying by 1 over x plus 3, right? That's just the normal fraction rule for dividing fractions. And now we can see these x plus 3's are going to cancel. Okay. So we get limit as x approaches -3 of 1 over x plus 2. So we get 1 over -3 plus 2, which is -1. Okay. And I just realized I didn't actually plug in -3 originally, but we can see if we plugged in -3, this would be -1 plus 1 is 0, and then the bottom would also be 0. So we would indeed get 0 over 0.